I plan to discuss on different methods to do scoring. Scoring, by scoring, I mean once you do your simulation, you set up your physics, you set up your geometry, and uh, in the source particle source. Now is the time you want to know how much is the dose deposited, how much is the dose deposited in water, how much is the dose deposited in medium. So, or maybe you are interested in computing how much is the photon fluence or any other kind of those scoring options that you want to explore. So today we will focus on this scoring module, and we won't be covering graphics, time feature, variance reduction, or other part of this because this much is more than enough for you for at this moment to start working with the Topaz or Monte Carlo. And in future, if will be it will, you require it, uh, I can talk to you, we can talk about this, and I can provide more workshop on this on Topaz
Okay.
simulation or other modules. Okay, so this is the
Okay.
last module that we are going to cover. So if we talk about scorers, we have different type of scorers available. So we have volume scorers, we will check shortly. Then is those to any material track length estimator. Like I said, it's a kind of a variance reduction technique that only considers collisional karma as uh, collisional karma to compute the absorb those. It do not consider the secondary particles emitted. So this kind of technique works for brachytherapy applications because the photons are not that energetic. Whereas if you are using high energy photons for like with the uh, MV beams, so maybe this won't work. So you should take care of when you are using these scorers. So either you go with those in material, and then you can do like radiation protection quantities. You can score like ambient dose equivalent, dose to water, dose to material, origin counts, charge or effective charge of for photonality, protonality, surface scorers you have, then phase space scorers. Like I mentioned, it is for high energy beams when you model LINAC heads or maybe proton therapy units, you might be using it. Um, then there are like ways to filter your scores. For instance, you want to know only the dose deposited. Let's say you are using simulating a patient geometry and you only want to simulate how much dose goes to bladder. So there is a way to do it. You want to know how much is a dose that is going only to the tumor volume. There is a way to do it, and you can apply filters for it, and it works. Then output specifications can be either you can get the Excel file of your output, or you can use a DICOM format. Our example, this workshop example takes a DICOM output. So we are working with the DICOM output, and then you can output a histogram, dose volume histogram, phase space. Then you can bin means you can voxelize your whole geometry, whole thing into several type of components like cube boxes. You can do energy binning by energy, by time, time feature. So there are different possibilities that you can use for your simulation or your experiment that you're simulating. So let's get started. Initially, there are mainly two basic scorer. One is the volume scorer and another is the surface scorer. So if you want to, whenever you use your score, define your scorer, you have to define what quantity uh, you want to compute or score. Like in this case, it's a dose to volume medium. And then do you want to do the when your scoring component is the parent, like for instance, um, parent is the world volume. Okay, like in our case, if we consider our geometry, let me go here, service. Okay. So in our geometry, the world volume is the parent, and then all other volumes like the boxes and this yellow meshed bin, the geometry or the score, all of them are like the parent of these geometry is world volume. And you can observe this from our input file as well. So if you see the first box over which you we place our in the box where that is our shield, it is the parent is world. Then you do take a look to the source placement box, it is world. And then the parent is world. Again, if you look at the tumor, the parent is world. So this is what they're saying, like when your scoring component is world, when you do the scoring in the whole of your world volume, uh, uh, scoring component is parent of other is the parent of other components like you are scoring in the world. You have an option to set scoring to record only in a parent not only in the parent, you can do calculation in everywhere. So when you start scoring in your world volume, you can score in each and every part of that, like shielding the box that contains the source and uh, the box that is made up of water. So you can do scoring by setting this propagate to children. And one thing I would like to clarify here is you will think about the if it is possible directly to place the source below the shield. Why I added this air box? It is to show you the concept of parallel geometries, like how you can place a seed inside a volume. Otherwise, if you don't use a parallel geometry, it will you won't be able to place a source inside this volume. Then it will start showing that you have a overlap with other volume. Like now, if you try to place the source without parallel world concept, it will show that you won't be able to run your simulations because it will keep on complaining that your world volume or the your geometry has an overlap, and Topaz won't provide you accurate results if there is an overlap or if you are not using the uh, this parallel geometry concept. Okay, so yeah. And then you can
Okay.
and there is a way like you can maybe there is a possibility you are interested in some other quantity or you want to score something else than what is provided by the topaz. So there is a possibility for you to add your own scorers. So uh, there is a way, and here is how you can do it. There is like you define your scorer, your units, and all. So we'll and you have to actually write C++ code for it, and uh, and then you can extend Topaz as per your requirements. But it is really advanced for you right now, so we'll stick with whatever is provided by Topaz. Okay. So the quantities that you can
Mm-hmm.
score with the volume scorer are those to the medium, those to the water, those to any material, and it tells about how it calculates this, and then is the track length estimator. to calculate those calculated using track length estimator technique. uh, yes, these are the different scores available. Then it's like energy fluence, energy deposited, effective charge, photoprotonality that you might be interested in computing. So, yep, these are the different scores available. Then you have to specify in which component you want to do the scoring. So we will look at I have decided to check with you three or four examples on like this kind of scorer, how you set the scorer, how it outputs, and we will run one or two simulations with it as well. So yeah, then you have to define the component, like I discussed earlier. You have to test if you want to compute for everything. You can set to propagate to children true, and then it will compute those or the quantity you are scoring to all the components. Then those two material, then you have to specify which material you want to compute this dose. And there is to check what material has been defined, you can use uh, this command, like integer material verbosity. So it basically is used to output anything on your running screen. And then here they define about the track length estimator, doses calculated. Yeah, like I said, it considers collisional karma only, and they do not consider the secondary electrons or uh, other components or of uh, the spectrum to compute the dose. Yes, and here is the example for it. Then is the ambient dose, like yes, and dose to water and dose to material, and yep, origin count, charge and effective charge, protonality. I'm going superficially through these because we won't be using them in this tutorial, and if you are working with brachytherapy simulation, you won't be using them either. So then
Okay.
there are like surface scores, then like surface current, surface track count, phase space. So like I mentioned in our previous meeting, like phase space is nothing but you define a plane at which it is a very actually a XY plane where you want to store the information of your charge particle that are emitted from the Linux head, and it contains all the information like their position, their momentum, are stored in one plane, and it's a form of surface core. So yes, you have to indicate a surface here, which surface you want to, at what surface you want to compute it, and then you can make it propagate to children. And so you have to specify some things like if we are using a surface score in the form of TS box, so you have to define x minus surface, x plus surface, y minus, y plus, z minus, z plus. Similarly, there are like two cylinders you can define. To specify surface depends on the shape. Yeah, so it's just like which surface you are defining, and each surface, for each shape, there are several options for you. Uh, Water tank. Yeah. Now coming to phase space score, so probably we won't be touching it. It's mainly for you can do it for your simulations as well. Like let's say if you are, but I don't think it will be more like you will need. uh, phase space